With the last session of the multi-robot and area systems. And so the first paper is about the graph attention multi-agent fleet autonomy for advanced air mobility.
Hi everyone, my name is Madin Fernando. I'm a PhD student from Indiana University. I'm presenting Graph Attention Multi-Agent Fleet Autonomy for Advanced Air Mobility. Advanced air mobility is transporting passengers and cargo using different types of electric vertical takeoff and landing vehicles. With the recent developments of aerial robotics, this came into a lot of interest, and companies have come up with some extremely innovative drone designs. As a result, the Federal Aviation Agency predicts there will be about 1 million different kinds of drones by 2027. And all of these drones are going to be different in their payload type, size, and the range. Also in mobility systems, we have depots. They are also going to vary in their demand patterns and the payloads. So if we put these two things together, they are going to give rise to a large number of heterogeneous interactions. So a natural question is, can we explicitly absorb these heterogeneous interactions into decision-making frameworks and use them to learn more generalizable reinforcement learning policies? The existing work on autonomous mobility mostly focuses about centralized passenger assignment for maximizing the fleet's revenue. But we want to delegate this autonomy toward the agents. The existing multi-agent-based approaches require complete information about the mobility system. But that's a very difficult thing to do if these vehicles are being managed by multiple parties and under real-world communication constraints. So we propose a multi-stage game for autonomous mobility. In the first stage, autonomous mobile agent observes its local environment. And next, it uses this observation and a trained policy to choose a depot from the mobility environment. The vertical bars next to the depot indicate there are different types of payloads. Next, depot can use its own payload assignment policy to assign a payload to the vehicle. Finally, the vehicle travels to the depot, picks up the payload, delivers it to the destination, and collects a net revenue. So in that way, we can account for different levels of heterogeneity in multi-agent systems and mobility systems. In our approach, we use these local observations to create a heterogeneous interaction graph. Next, we pass this graph to a graph attention encoder. Inside the encoder, we learn 5 different types of convolution operators and attention coefficients. The idea is to quantify 5 different types of previously identified interaction operators. Then we pass down the projected features to a decoder. Inside the decoder, we again learn 4 different types of interaction operators. The outputs of the decoder are the probabilities associated with each of the depots. Next, we mask the depots that does not carry any suitable payloads for the vehicles in the vicinity, and we choose the depot that maximizes the vehicle's long-term expected revenue. The big picture is that if we can learn a policy by quantifying a finite set of interactions in the mobility network, then this policy will also be applicable to a different mobility environment that builds on the same set of interactions, regardless of its size. This is a custom-built multi-agent reinforcement learning framework for mobility environments. One problem with MARL is it can be notoriously slow. So during the training, we skipped all of the time steps that an agent does not have to make a decision. So in that way, we could also prevent collecting unnecessary information in the training buffer and speed up the simulation. We followed a zero-shot transfer approach. We first trained this policy in a non-on-demand environment and transferred that to an on-demand environment. The objective was to force the agents to explore the environment more when it becomes increasingly resource scarce. We tested our approach in 2 settings, one high-yielding on-demand environment and one previously unseen low-yielding on-demand environment. In both of the environments, our approach was able to outperform other graph neural network policies. And most importantly, it was only 6% behind the centralized payload assignment method that we considered, which is actually pretty impressive considering that our approach is completely decentralized and only requires partial observations. We also tested the generalizability of our approach by changing the fleet composition, number of depots, and number of clients. And throughout the experiments, it gave us pretty consistent results. And this is my favorite of all of our results. When we increase the number of observable depot percentage, the attention encode decoder was able to absorb this information and increase the fleet revenue accordingly. For more results, I would like to invite you to our poster. So the take-home message. In this work, we laid the groundwork for learning more generalizable policies in multi-agent environments and mobility environments by considering multiple layers of heterogeneity and partial observability. In our future work, we are also considering minimizing the optimality gap by giving the agent some kind of a centralized trigger. That's all from me. I would like to ask any questions if you have, or please visit us during the poster session. Thank you.
Okay, thank you for the talk. And yeah, we have time for a couple of questions. So, any questions from the audience? In front?
Hi, so thanks for the talk. So in my experience using graph attention, like I found the memory consumption and also the inference speed seems to be like a huge issue for me. So in your case, does those like pose any issue for this system?
Yeah, thank you for this question. Actually, yes, graph attention can be extremely slow to train as well. When you actually put heterogeneity into the account, so it's actually getting even more worse. So one of the things that we did was that active time step simulation, which means that each agent goes through its own state machine. So in that way, we can actually eliminate collecting some of the observations. For example, if an agent is not in the available mode, say available mode is when it can actually apply for a payload delivery, right? So if it is not in a payload delivery mode, then we do not actually collect observations for these agents. And we do not also update the game, right? So in that way, we can like sort of speed up the simulation, but agents do maintain their internal state. But as a whole, the game is not being updated. But when the system reaches to the next active time step, that means if there will be at least one agent in the system that is in an available mode, that's when we start updating the game again. So in that way, like we are not actually collecting that many observations.
All right, thank you.
Okay. Any other questions from the audience? I have a quick question. So for your problem that each vehicle can carry only one payload?
Yes, we do not consider the shared autonomy at this moment, but we have 3 types of payloads in the system: small, medium, and large. Also 3 types of robots. So large robot can carry a small or medium or large, but the small robot can only carry the small type. So there's some sort of heterogeneity, but we don't consider the shared mobility. One excuse that I tell you, because when it comes to aerial mobility, we do not actually have the infrastructure, or it's also going to be a much more difficult problem compared to the urban mobility.
Okay, so I think that would be a very interesting direction to consider some capacity of the vehicles and so on.
Yes.
Okay, cool. Do you have any other questions from the audience? So if not, let's thank the speaker again.